The first question asks us to complete this table about subatomic particles. So atoms are made of protons, neutrons, and electrons. Protons and neutrons are found in the nucleus, whereas electrons orbit the nucleus in energy levels. Protons have a positive charge, +1 for each proton. Neutrons are neutral, so 0 charge for each neutron. And electrons have a negative charge, so -1 for each electron. The next question asks us to complete a table about different isotopes. So first, when the element is written in the symbol notation, we put the mass number on top and the atomic number on bottom. We can also write it in its element name notation, so we put the element, a dash, and then we write the mass number. The atomic number is the same as the number of protons. You can often look that up just using a table of elements. The mass number is the sum of protons and neutrons. Those are the big, heavy, massive parts of the atom. And for charge, we have to look at the charge parts of the atom. So those are protons and electrons. So my first isotope here, we know that it's hydrogen, 3, because we have the symbol, and we know that the mass number is 3. So since this is hydrogen, the atomic number is 1, and the number of protons is also 1, because they're the same thing. My number of electrons is going to be 1, because 1 positive proton plus 1 negative electron gives me a charge of 0. My mass number is 3, and since one of those is a proton, the other 2 must be neutrons. The next isotope is cobalt-59. So I can find the atomic number and the number of protons just by looking up cobalt on the periodic table. This particular cobalt has a mass number of 59, which means that I must have 32 neutrons, because 27 protons plus 32 neutrons gives me 59 as my mass number. My charge is -1, so that tells me that I have 1 more electron than protons, so I've got 28 electrons. Now I can put it all together into the element symbol. I need to include the mass number, the atomic number, and the charge. Isotope C has an atomic number of 1, which means that it has 1 proton. Since the mass number is equal to 1, and that's a proton, there must be 0 neutrons. And since I have +1 protons and no electrons, my charge is +1. So I can write the element name as well as the symbol. For the symbol, I need to include the mass number, atomic number, and charge. And for the element name, I need to include the mass number. Next is isotope D, which has an atomic number of 27, which means that we have 27 protons. So this is also cobalt. The difference here is that my mass number is 93. So that means that I must have 26 electrons in order to balance out my 27 protons. So we've got 93 as our mass number because we have 66 neutrons. So when I write the element name, I need to include the number of protons and neutrons, the mass number. And if I write the symbol, I need the mass number, atomic number, and charge. Our last isotope here is isotope E. So isotope E has 28 protons, which means that its atomic number is equal to 28. There are 34 neutrons because 28 plus 34 add up to give me 62 for my mass number. Given that I have 28 protons and 30 electrons, I have 2 more electrons than protons. The charge on this one is going to be -2. So to figure out which element this is, I just have to look on my periodic table, and atomic number 28 is nickel. The next question asks, which of these letters represent isotopes? So isotopes are the same element, they have the same protons, but they have differing numbers of neutrons. So isotope A and C are both isotopes of hydrogen, and B and D are both isotopes of cobalt. Cations are any atoms that have a positive charge. There's a T in cation, which is kind of like a plus sign. So my cations are going to be isotopes C and D, and my anions, therefore, have a negative charge. That's going to be B and E. In an isotope, the number of protons / atomic number is always the same, but the number of neutrons or the mass number also varies. So given the isotope here in number 5, how would we determine the number of neutrons and the number of protons? So first, the top number is the mass number, which is the sum of protons and neutrons. The bottom number is just protons. So if you subtract the two, you can get how many neutrons there are. To get the number of protons, you just simply look at the atomic number which is given to you. In the next question, we need to calculate the average atomic mass of bromine. So we're doing a weighted average here, which means that we have to take into account the relative abundance of the different isotopes. So I need to take the percentage of the atomic mass for each isotope and then add it together. So for my first isotope, 50.69 of all of the bromine has a mass of 78.92 AMU. So I need to do 50.69% of that mass. And I'm going to do the exact same thing with my other isotopes. So this one has an abundance of 49.31 and the mass is 80.92. So once I get these two numbers here, I just need to add these up in order to get the weighted average. So once I have this number, if we know what element this is, we can look at the periodic table and just confirm that it matches. So we have a built-in way to see if we did this correctly. Now in the next one, this is a little bit different because I didn't tell you what the element was. So that trick I just showed you where you can check the periodic table, it's not going to work if it's you don't know what element it is. So in this example, I've got 3 isotopes, A, B, and C. And I'm going to want to do the exact same calculation for all 3 of them. I want to know the product of the decimal abundance and the atomic mass. Once I get all of those answers here, I can add them all up and get my final molar mass here, my average weighted mass. It is important to note that 9.7, remember that whenever you divide by 100 that you're moving the decimal over twice. So that would be 0.097 once you did the division. The next question asks what elements are found in the mixture below. So the way that we're going to go about doing this is we need to match the lines. And any of the known elements that completely match what I have in my mixture, that lets me know that those elements are present. So I think the best way to do this is just to get a highlighter. And all that I'm doing here is highlighting ones that are the same. So now that we've done that, we see that the only ones that completely match the mixture is going to be lithium and strontium. So because the bright line spectra for lithium and strontium match the mixture, these 2 elements must be present in the mixture. Question 9 says, on the bright line spectrum, lithium emits and absorbs light at 4 wavelengths. Using the scale provided, determine the wavelengths of the 4 emission lines to the correct precision. So this scale goes by 100s, which means that we have to guess the tens place. So my first emission line, I'm going to say is about at 670 nanometers. My next one is about 610, just a bit past 600. My next one is a little bit before 500, but the precision of this only lets me guess to the tens place. So I'm going to say that this is 500. And then my last line here, closer to 500 than is to 400, I'm going to say about 460 nanometers. Next, we want to rank the wavelengths from least energy to most energy. So long wavelengths give us low energy, and short wavelengths are higher energy. So energy is equal to h times frequency. So the bigger the frequency is, the bigger the energy will be. So in order, we need to start with our short wavelengths and go to our long wavelengths. So my shorter wavelengths are going to be high energy. They're going to have the most energy, whereas my long wavelengths will be the lowest energy. Why does lithium emit light at the given wavelengths, and displayed in terms of electron transitions? So this goes back to the Bohr model of the atom. So here's a very simple atom, a lithium atom, and we're only showing one electron here. This electron is currently orbiting the nucleus in its ground state. So that is its normal energy level. It's possible for it to absorb some energy, in which case that electron is going to jump up to the excited state. So here we jumped from the first energy level to the third. It could have been the first to the second, or the second to the 20th, or the second to the third. All of those transitions are possible. So electrons absorb energy and jump up in energy level. This excited state is unstable. So to regain stability, electrons relax back down to the ground state by releasing energy in the form of electromagnetic radiation. So we see this with our eyes as light. Then the electron, having lost that energy, returns back to its ground state. So the energy of these transitions matches the energies and wavelengths that we see on the bright line spectrum. So the bigger the jump, whenever it falls back down, the more energy is released. This is going to be my short wavelength, high frequency type of electromagnetic radiation. How does this relate to the flame test? So during the flame test, the energy from the flame excites electrons, causing them to jump up to the excited state. Electromagnetic energy is given off by those atoms as their electrons relax back down to the ground state. Our eyes are able to detect some of those energy transitions. These are the ones which fall on the visible light portion of the electromagnetic spectrum. Now we need to convert the biggest and smallest wavelengths into meters, and we want to write our answer in scientific notation. So we have 460 nanometers and we have 670 nanometers. Those are my biggest and smallest wavelengths from answer A. So I'm going to start by putting them over 1, and I need to convert nanometer into meter. So I'm going to put nanometer on top and meter on bottom, and then I'm going to fill in the conversion factor. So 1 nanometer is 1 times 10 to the negative 9 meters. And when I solve, I get 4.60 times 10 to the negative 7 and 6.70 times 10 to the negative 7. So whenever you're writing this in scientific notation, since both of these are small numbers, they're going to have negative exponents. So we had to move the decimal over until there was only one number in front of it. So I want 4.6, not 46. The next question says to explain what redshift and blueshift are and what they tell us about galaxies. So redshift and blueshift describe how light shifts towards shorter or longer wavelengths as stars move closer or further away from Earth. So an example of this would be the Doppler effect. If you hear an ambulance approaching you, as it approaches, the pitch increases and it gets louder. As it moves away, the pitch decreases and it gets quieter. So instead of it being pitch that changes, it's the wavelengths of light that get longer. So when a star moves away from Earth, the wavelengths of light from the star get longer, shifting towards the red end of the spectrum. If a star was moving towards Earth, the wavelengths of light would get shorter, so shifting to the blue end of the spectrum. So because all of the light that we see from distant stars is red shifted, this tells us that all of these galaxies are moving away from us, which means that the universe is expanding. Number 11 asks us to define some variables. So V is the speed of light, which is velocity. F is the frequency, which is in hertz. And lambda, this Greek letter, is for wavelength, and that's in meters. And that makes sense because it's a length. We measure length with meters. The speed of light has units of meters per second. So whenever you do wavelength times frequency, you get the same units. For the other equation, E is for energy. H is a constant called Planck's constant. and it is 6.626 times 10 to the negative 37 joule seconds, and the frequency is per second. So whenever we multiply H and F, the seconds cancel and we're left with joules. As the wavelength of electromagnetic radiation increases, the frequency is going to decrease, whereas the energy will also decrease. So as those wavelengths get longer, if I stood at one point and watched the waves go by, longer wavelengths means less waves are going by, so the frequency is lower. We know that E is equal to H times F, so if frequency is lower, then energy will be lower as well. Number 14, the wavelength of some electromagnetic radiation was measured to be 3.50 times 10 to the negative 7 meters long. So to calculate its frequency, we want to use V equals F times lambda. We know V is the speed of light, F is what we're solving for, and we know that the wavelength is 3.50 times 10 to the negative 7. So I'm just going to plug this into my equation here, and I'm going to solve for frequency, and I get 8.57 times 10 to the 14 per second. So this is how many times the wave passes per second. It's also written as hertz, Hz. So now that we know the frequency, we just solve for that. If we multiply it by Planck's constant, that's going to give us the energy. So when I solve this, I get 5.68 times 10 to the negative 19 joules. So where does this belong on the electromagnetic spectrum? Well, based on a wavelength of 3.5 times 10 to the minus 7, this is going to come in just before visible light. So it's a little bit in the ultraviolet range.